1.2 Radioactivity. Let's begin. A radiation detector. The picture shows a radiation detector for gamma radiation. In this chapter, you will see other radiation detectors and use them to investigate the properties of different types of nuclear radiation. 1. Sources of radiation. A. Background radiation. We can never avoid nuclear radiation, as a part of it comes from natural sources. This is called background radiation. For your information, the background radiation in Hong Kong is about 100 counts per minute, or 0.24 sievert per hour, which is at least 2 times that of Tokyo. B. Radioactive sources in school laboratory. The school has weak sources like americium and radium for physics experiments. They are shielded sources with wire gauze to avoid direct contact. School laboratory safety for the use of radioactive substances. Radioactive sources are stored in lead container with warning signs and locked in a safe. When handling radioactive sources, we use special lifting tools, which is a pair of special forceps. Do not direct the source to anyone and do not try to examine the source directly. Lastly, these experiments should be as short as possible, with careful planning beforehand. Lastly, these experiments should be as short as possible with carefully planning beforehand. 2. Ionizing power. Ionizing radiation can cause ionization, which means produce ion pairs. Ionizing radiation is so energetic that it can lock off an orbital electron from an atom and produce an ion pair. If it is a gas molecule, the gas is said to be ionized. With the ions, the gas may conduct electricity. If the radiation is stronger, there will be more ions and the gas will become more conducting. Nevertheless, different types of ionizing radiation have different ionizing powers. A spark counter counts the number of radiation when they produce ion pairs. The voltage between the electrodes, which are the anode and cathode, is high, but just a bit lower to ionize the air directly. When ion pairs are produced, the ions are attracted by respective electrodes, and sparks are produced when they strike on the electrodes. When more ions are produced, more sparks will be produced.
In this experiment, we will compare the ionizing power of alpha, beta, and gamma radiation using a spark counter. Connect the spark counter to an EHT supply. Gradually increase the voltage until sparking occurs. Then reduce the voltage slightly so that sparking just stops. Hold an alpha source about 1 centimeter above the wire gauze. Observe the sparks produced. Repeat with a beta source. Then repeat with a gamma source once more. Which kind of radiation produces the most sparks and therefore has the strongest ionizing power?
From the experiment, we can see that the ionizing power of alpha is the strongest, followed by beta, and gamma is the weakest. Alpha radiation is a stream of helium nuclei, each carrying positive 2 units of charge. The charge is largest in the 3 main types, and alpha particles also move slowly. These 2 factors explain its strong ionizing power. Beta particle is a stream of electrons, each carrying 1 unit of negative charge. It is moving fast, close to the speed of light, and that explains its weaker ionizing power. Gamma radiation is an EM wave carrying no charge and moving at the speed of light. And that's why it can hardly produce any ion pairs. Also, sparks are observed randomly, and therefore nuclear radiation is emitted at random. This is called random nature of radioactive decay. Example 1. Ionizing effect of nuclear radiation. The setup makes use of the ionizing power of beta radiation. When the ions produced are attracted by the conducting plates, which are the electrodes, there is current flow. The current flow will be larger if there are more ion pairs produced, for example, when an alpha source is used instead. Nevertheless, there will be no current produced in vacuum because there is no air in vacuum to be ionized. An ionization chamber has a similar design as the setup in example 1. A source with a stronger ionizing power will produce a larger discharge current.